In this unit, we're going to go through some quadratic patterns and some function notations. But first, let's take a look at a review question from last week. So here, I have a multiple choice question where I'm asking you to compare the slopes and the y-intercepts of the graphs below. And so what we can see here is that I clearly have three different slopes. I don't need to calculate these slopes. I see that the slope of r must be a positive value, and that's because the graph is increasing, whereas the slope of q must be negative. The y values are getting smaller and smaller as we read the graph from left to right. And with the function s, there is no change in y for whatever change in x we have, and therefore the slope is 0. So here we have a positive slope, a negative slope, and a slope of 0. So right away, I can look at the slope values and I see r is greater than s, which is greater than q. And so the answer is C. I didn't need to calculate anything here. I can just do this by inspection. To double check with the y-intercepts, what I can do here is I can recognize that y-intercepts mean the value of y when x is 0. And so it's, in other words, where it crosses the x-axis. And I see that q crosses the x-axis at the highest point. So y would be the greatest value for q, then for s, then for r, which is exactly what this says. So in this question, you didn't have to calculate anything to answer the question correctly. Here's another question on linear functions, which graph has a slope of 1/3. And again, just by looking at this, maybe I'm not able to calculate this well, but what I can see here right away is that B and D are parallel lines. And so they can't have they would have the same slope, and therefore it wouldn't be the graph that has a slope of 1/3. So really now it's down to C or A. And if I look closely here, a slope of 1/3 might be difficult to look at, but or might be difficult to identify. But what would make it easier is to look at this in terms of a change in y over change in x. And this is 1/3, which means every time the x value is changed by 3, the y value is going to change by 1. So if I look here at the C graph, now this graph isn't drawn perfectly, but I can see that I'm going over 3 and up 1. And I do that from anywhere, over 3 and up 1. Whereas in A, I'm clearly going over 3 and then up more than 1. And so the answer here again is C. And of course, this just is further evidence that every multiple choice answer is C, except on your midterm and final. In any case, these two happen to be C. So here's a starter, a question, more or less a review from last week. Find the equation of the line that passes through the points -3, 5 and 4, -44. One of the things that I always suggest to my students is that they look at what the answer is going to look like. Now, I'm not suggesting that you look at this and know the answer, but realize what you're looking for. You're looking for an equation of a line, and there are many ways for us to represent that, but we've only talked about y = mx plus b. Okay, that's when I know I've answered this question correctly, is when I have that as my form. So I need the slope and a point to solve that. And so we can quickly find the slope, because that's the change in y divided by the change in x. And so I have two y values, and so what I'll do is subtract those, and I have my two x values, and I'll subtract those. And remember, it doesn't matter if you put this 5 first or second, as long as you put its corresponding x value in the same position. There's the data point, -3, 5. So the slope here is -7. What that means is that my equation now looks like this. Y equals -7x plus b. So I need to find this b value. And in order to find the b value, I'm going to need an x and a y. And of course we have a couple of those. We have an x and a y here, and the x and the y here. So it doesn't matter which one of those I choose, I'm going to get the same value. And so if I plug in x equals 4 and y equals negative 44, I add 28 to both sides, I get b equals negative 16. If I do the same thing with the other point, plugging in x equals negative 3 and y equals 5, I'm going to get the same value. So the equation here is y equals negative 7x minus 16. And I've drawn this out on a graphing program, and you can see that these are my 2 points located here and here, in case you didn't believe me. Okay, so now we're on to some patterns, which is another way to represent the linear functions that we talked about. So if you look at this pattern, you obviously can figure out what the next term is. And by looking at that next term, you're already looking at this equation. You're looking at this pattern in terms of an equation, whether you realize this or not. And we're going to do the same thing, but in order for us to do the same thing, we first have to be talking about the types of variables. The 2 types of variables that we'll have here are the term number and the term value. Very important that you get these straight. The term number talks about the position inside the pattern. So I'm going to talk about how many blanks am I drawing. So for instance, this 10 is the term number, has a term number of 3. It's in the third place in the pattern. Okay? Whereas the value, this is the number that I see. Okay? So the value of the third place is 10. The value that's in the fourth place is 13. So when the term number is 4, the term value is 13. And so this always comes down to whether I'm talking about how many blanks are in this pattern, how many spaces are in this pattern, or what numbers I see in the pattern. The numbers I see are the term values. So we can rewrite this pattern like this. The term numbers, 1, 2, 3, 4, that's the placement. The term values are 4, 7, 10, 13, as we talked about. And so we can clearly see here that there's a pattern. And the pattern arises from this common difference. We see here that we take 7, subtract 4, that gives me 3. Similarly, 13 subtract 10 gives me 3, and 10 subtract 7 gives me 3. So this is what's called a common difference. Now I'll be calling that a CD because that's a lot easier to write, obviously, than common difference. But in any case, what we have here is this common difference. Now, sometimes I'll use CD, sometimes I'll just use D. Really, I should use D because we don't technically put 2 variables in to represent one number. So let's take a look at rewriting this pattern in a different form. So here's the same numbers. Now that we recognize this common difference, what we can start to look at here is say, I can rewrite this pattern as 4 plus 0 times 3. So that's just 4, my first term in the pattern. Or I can say, I can add 3 to it 1 time to get 7. Or I can take that 4 and add 3 to it 2 times to get 10. Or add 3 to it 3 times to get 13. And so what happens here is I can then start to predict what's the, for instance, what's the 100th term. Well, what you see here is that when I had n equals 4, I was adding the common difference 3 times. When I had n equals 3, for the third term, I'd already used up a term, and then I had 2 more terms to go. So I added 3 twice. So in this case, what will happen is I'll have 4 plus 99 times 3. I will add 99 common differences to the first term, and there's my 100 terms. So what we see here is that I can get any term number I can get the term value for any term number using this equation. And so this 3 was the common difference, and this 4 was the first term, which we'll call T1, or A. I'll usually use T1. So in general, when we have a common difference, what we get here is an equation that says Tn equals T1 plus n minus 1 times D. Now this isn't exactly how I'd leave the pattern. I would actually ask you to multiply this out, but we'll talk about that in a second. So let's take a look at finding the general rule or equation for the following pattern. So the first thing I have to recognize is that there is indeed a common difference. And the common difference here is negative 4. Remember what that is 1 minus 5, negative 3, subtract 1, and negative 7, subtract negative 3. Then I recognize that the first term is the 5, and so I can plug this into my equation. Now again, I'm going to multiply this out. Oops. Negative 4 times the n, and negative 4 times negative 1. This will give me Tn equals 5 minus 4n plus 4. I can add the 5 and the 4 together, and I get Tn equals negative 4n plus 9. Now because I have this equation now, I can find anything about this pattern. Okay, remember, math is about, really comes down to representing same information in different ways. So this pattern is now represented like this. And this actually looks an awful lot like y equals mx plus b. We're not using y and x's here, because if I have this graph, this means that x could be anything. X could equal, for instance, 0, or x could equal negative 2. Or x could equal 7.3. But it doesn't make any sense when I'm talking about the term number to talk about a number, a term number of 0. I can't say what's the 0th term here, or what's the negative 2th term, or what's the 7.3th term. So when we have values that are going up by, starting at 1 and going up by 1, what we usually call that is an n value. So n here can be 1, 2, 3, 4, 5, because it makes sense to talk about the 5th term of the pattern, for instance, but not the 5.1 term, or the 5.1th term. So now that I've represented this equation, or this pattern in an equation, I can now use that equation to predict things. This asks what's the 100th term of the pattern above. What you have to recognize is what this 100 is. Is it there are 100 spaces in this pattern? Or is this asking how many numbers will I write until I write the number 100 in this pattern? Do you see the difference there? Take a moment and think about that. I'll say it again. Are there 100 spaces in this pattern? Or is it asking how many numbers do I write down until I write the number 100? And what this is saying is, it's asking what is the 100th term. So this is asking what is the 100th number that I write down. I'm not going to write down the number 100. I'm going to write down 100 numbers. And so this means n equals 100. So I have the same equation, but n equals 100. So wherever I see an n, I'm going to plug in 100. And so very quickly, instead of doing this out all the time and going and going and going 100 times, I can very quickly tell you that the 100th number that I write down in this pattern will be the number negative 391. So the term value is negative 391 for the term number of 100. Now this is a slightly different question. How many terms are there in the following pattern? Well, the first thing you have to do when you find a pattern is you have to talk about what type of pattern it is. We've only seen one type of pattern so far, one where the common difference occurs right away. Negative 6 minus negative 9 is 3. Negative 3 subtract negative 6 is 3. 0 subtract negative 3 is 3. So here I have a common difference of 3. I have the first term of negative 9. I can plug this into my equation. Don't stop there. Make sure you simplify. Okay, that's just for good practice. So right now I have Tn equals 3n minus 12. I can test this out. I can put in n equals 1, 2, 3, 4. If I put in a 4 here for n, I should get a term value of 0 because that's what's in my pattern. And of course I do. 3 times 4 is 12. Minus 12 is 0. But that's not what this question is asking. This question is asking how many terms are there in the following pattern. So how many terms I'm looking for the n value, which means I must know the last term in the pattern. And you can see that this pattern ends, that's why there's a decimal there, or a period there. This pattern ends with the number 81. So now I can plug in 81 into this and start solving for n. I'll undo what's being done just like we did last week. I'll add 12 to both sides, and then I'll divide both sides by 3. And what I see here is that there are 31 terms in this pattern. If I wrote this pattern out, if I started at -9 and added 3 each time, I would write down 31 numbers, and the 31st number would be 81. So you can take a moment now and try these. Maybe it's a good time to pause the recording and practice these. I'll go over the answers in a moment. Alright, so let's take a look at these answers. Again, what we have to recognize is first find the common difference. In this case here, -10 subtract -8 is -2. -12 subtract -10 is -2. And so I have a common difference of -2, which means the equation is Tn equals T1, -8, plus n minus 1 times d. I'm going to multiply this out. This gives me -8 minus 2n, and -1 times -2 is plus 2. So the equation here is -2n minus 6. I can find the next equation. I can see that these numbers are actually increasing, whereas these ones were getting smaller in A. In question B, they're getting bigger, so I know the slope is going to be, or the common difference, I should say, is going to be positive. And I see that the common difference is 4, so I have Tn equals 1 plus n minus 1 times 4. Again, I'm simplifying here. 1 plus 4n minus 4. And so I have Tn equals 4n minus 3. In question C, I have a similar relationship here. I see the common difference is 0.5, and the first term is also 0.5. And so what happens here is I multiply this out. Goodness, sorry about the writing here. That doesn't like this -1 that I'm writing. This n minus 1 times 0.5, the common difference. When I multiply this out, I'm going to end up with Tn equals 0.5n. So now it's asking in question B to find the 50th term. So what's happening here is that this is n equals 50. I'm asking to find the value of the 50th term. So wherever I see an n in these equations, I'll plug in n equals 50. So for A, I have Tn equals -2 times 50 minus 6. This is going to give me -106. For question B, I have Tn equals 4 times 50 minus 3. This 4 times 50 is 200, minus 3 is 197. And for question C, I have Tn equals 0.5 times 50, and so that's 25. Now, question 3 asks, which term has a value of 59? And so I'm going to find the value of the equation. I see that the common difference here is 3, and so the equation is Tn equals -4 plus, let's see if I can do this, n minus 1 properly, n minus 1, there we go, times 3. And so what this ends up being is, I'll continue this down here, I guess, is Tn equals 3n minus 7. So now I'm going to figure out which value, or sorry, which term has a value of 59. So this is my Tn value, and I'm going to solve for n. I'm going to add 7 to both sides, 66. I divide both sides by 3, and I see that the 22nd term would have a value of 59. Now question 4 is very similar, except instead of giving you the pattern, I've already gave you the equation. So for question number 4, what we're going to do is we're going to plug in -85. So -85 equals -2n plus 1. I think that's what I had anyways. 2n minus 1. So what I'll do here is, again, I'm undoing what's being done. I'm going to add 1 to both sides to undo the subtracting 1. This gives me -84 equals -2n. Divide both sides by -2, and I get n equals 42. So the 42nd term in this pattern would have the value of -85. So let's take a look at some deeper patterns now. And so if we have this pattern 10, 18, 28, 40, 54, your first inkling is to find the common difference by subtracting, and that doesn't look like it's common. But of course, if you investigate this pattern a little bit, you'll see that in this first level of difference, there is a pattern. And the common difference of the first level of difference is 2. So here is the first level of difference. I think that's for obvious reasons. And this is the second level. And so what we have to do here is we have to figure out what this common difference means. Well, we certainly realize that it's not going up by the same amount each time, so it's not a linear equation. And so we'll have to figure out what type of equation we're going to do to fit this. And these are called quadratic equations, the equations that will model these quadratic patterns. And so what we see here is that every quadratic pattern can be represented by the equation. Well, wait a second, that's not what we have, because that's for a linear pattern. We can't use that now. The common difference wasn't on the first level of difference. So what we have here is Tn equals an squared plus bn plus c. So what we will define here is the a, the b, and the c value. Remember, when we were doing this with the linear patterns, what we had to define was the a, or the t1, and the d value. Those are the constants. Once we found those, we had the equation. Well, for a quadratic, it makes sense that we would need to find more than just 2 things, because this is a deeper pattern, so we need to find 3 terms, a, b, and c. And so each quadratic pattern has a different a, b, and c value. So for instance, here's a certain quadratic pattern. -4n squared plus 3n plus 1. That would have a different pattern than this. Tn equals 5n squared minus 3. Here the b value is 0. So what we have here is the equation with three constants to figure out. What we want to look at here is how does the common difference fit into the equation. Okay, so it was clear with the linear patterns that it fit in right here, but not so much now with the quadratic. So let's pause for a second, and I'll show you an example of what I mean. Let's take a pattern. Let's say 3n squared plus n minus 5. I just made that up. I'm gonna find the pattern that goes with this. So I'm gonna find n values at Tn. Well, the n values are gonna be 1, 2, 3, 4. Let's say I could go up as much as I wanted to. Tn, to find that, I'm gonna plug in the n value in all these spots. So the first one here is going to be 3 times 1 squared plus 1 minus 5. So what I have here is 1 squared is 1, times 3 is 3, plus 1 is 4, minus 5 is negative 1. That would be the first term. When I plug in n equals 2, I get this equation. 2 squared is 4, times 3 is 12, plus 2 is 14, minus 5 gives you 9. When I plug in n equals 3, it's in a different color so you can see what we're doing. 3 squared is 9, times 3 is 27, plus 3 is 30, minus 5 is 25. So I'm just developing the pattern here, and if I look at finding the fourth term, what I have here is 16, that's 4 squared, times 3 is 48, plus 4 minus 5 gives you 47. So here's the pattern. Let's see where what the common ratio is, or common difference is. So I'll just rewrite this pattern. And hopefully I haven't made any mistakes in my algebra here. We'll find out in a second. I'll find out in a second. Because I know what the common difference should be here. So let's find the common difference. 9 subtract negative 1 is 10. 25 subtract 9 is 16. 47 subtract 25 is 22. Obviously this isn't common. I wasn't expecting it to be common. This squared is going to tell me that the common difference is not on the first level. 16 minus 10 is 6. 22 minus 16 is 6. There's the common difference. The common difference for this pattern is 6, but how does that relate to those A, B, and C values? A was 3, B was 1, and C was negative 5. Well, it's not very clear. And you can pick any quadratic you want. You could change these A, B's, and C's, and you'll get a different pattern, and you might have a different common ratio. Or sorry, common difference. And so what we need to do here is we need to find how the common difference relates to these quadratics. So we're going to look at every single quadratic. And when I say things like that we're going to look at every single one, that means what I'm going to do next is complicated. It means you don't have to do it yourself, but you have to follow along to see where this comes from. So we're going to take every quadratic, which is Tn equals an squared plus bn plus c. I'm not going to take the specific one that we just looked at. or even the specific one that we're dealing with in the question that we're trying to figure out, I'm using every single one. So I've got to use A, B, and C. So I'm going to find the first 5 terms. Well, to find the first term, anywhere I see an N, I'm going to plug in the 1. And so this would be A plus B plus C. I have no idea what that number is, because this is for every single quadratic. The second term would be 2 squared is 4 times A is 4A plus 2B plus C. The third term would be 3 squared is 9 times A is 9A plus 3B plus C. The fourth term would be 16A plus 4B plus C. And the fifth term would be 25A plus 5B plus C. So what we have here is the hunt for a common difference. I find the first level of difference. Notice that I have 4A subtract A, that's 3A. 2B subtract B is just B. And C subtract C is 0. And I repeat that, and I see that the first level of difference doesn't show a common difference. I'm not surprised by that. But certainly the second level does. And so what we just found was that the common difference for any quadratic pattern is equal to 2A. You'll see me write this a lot. Common difference equals 2A. I need to find A, B, and C to define the equation for my pattern. Well, as soon as I find the common difference, I just divide it by 2, and there's the A value. So let's go back to our example. We had these numbers, 10, 18, 28, 40, 54. And what we had was a common difference of 2. Well, now that I know that, the A is 1. So I am 1 out of 3, or I found 1 out of 3 constants. Here's the 1. The equation now is Tn equals 1n squared plus Bn plus C. Well, what I need to do now is find the B and the C's. So I can set up equations for B and C as long as I have N and Y's. N and Tn's. And of course I do. There's one, there's another. These are data sets, data pairs. So what I can do here is I can plug in N equals 1 and Tn equals 10, and I can get this equation. And that simplifies to be 9 equals B plus C. And there's lots of answers to that. There's lots of possibilities for B and C. So I'm going to need another set, another equation, and that's why I'll plug in 2 and 18. I could have plugged in 5 and 54, but I'll always plug in the first 2 because I like working with 1s and 2s. And those n values for the first 2 will always be 1 and 2. And so when I do this, I plug this in. 2 squared is 4 times 1 is 4. Subtract that from both sides, and I get 14 equals 2b plus c. So there are 2 equations with those 2 unknowns. Well, this is what we did last week. I'm going to subtract, and I will always subtract here to eliminate the c values. When I bring this 9 equals b plus c down here and subtract these equations, 14 subtract 9 is 5, 2b subtract b is just b, and the c subtract c is 0. So now I know my b value. I know my equation looks like this now. Tn equals 1, that was my a. 1n squared plus 5n plus c, I need to know that c value. Well, just like we did last week with elimination, I can use one of those equations now that I have b, and I can plug in b equals 5 to find that c equals 4. So now I have the equation that represents that pattern. So 10, 18, 28, 40, 54 should be represented by this pattern. So we can test this out. If I plug in n equals 4, I should get a value of 40. 4 squared is 16, 5 times 4 is 20, and add those together and then add 4, that gives me 40. So you get a little wow here. It worked. Because I know you weren't believing me. The 10th term, well, anywhere I see an n, I'm going to plug in 10. 10 squared is 100. 5 times 10 is 50. Plus 4, that's 154. Now I asked for the 11th term, which might sound like a silly question to ask, but what I want you to realize is the first two terms only differed by 8. Well, if I add 8 to 554, I'm going to get 162. But that's not the right answer, because of course the common difference is growing. Here, the difference between 54 and 40 is obviously not the same difference as 18 and 10. And so what we have is this growing difference. And that's the same thing you see here. The difference has grown again between the 10th and the 11th term. Now, with linear patterns, I asked you questions like, can you find which term has a value of 270? And we actually can't do that yet. The reason why we can't do that yet is I can plug in 270 in for Tn. I have n squared plus 5n plus 4. But I can't undo what's being done because there are two types of n's here. I've got n squared and n. And I can't add those. So that's a major problem for us right now. And it'll take us a week or two to figure that out. So let's take a look here. What is the 50th term of the pattern 6, 14, 28, 48, 74? So I can continue this pattern. It would take a little bit of time, but I could do that. You're not going to have a chance to do that on the midterm or the final. You're expected to find the equation. And to find the equation, you need to know what type of pattern you have. And so you find the common difference. 8, 14, 20, 26 is the first level difference, and then the common difference is 6. And that means right away I know two things. First of all, because the common difference is on D2, I know I have a quadratic pattern, and quadratic patterns are represented by this equation. Secondly, because the common difference is 6, I know the A value right away is 3. And so now I can plug in when n equals 1, t1 equals 6, and when n equals 2, t2 equals 14. There's plugging in the first two data points. Think about it as n on top here as we had it in the last example. I can get some equations. I can subtract those equations, and I get the b value. I can take this b value and plug it into either one of these, and that will give me my c value. And so now I have the equation Tn equals 3n squared minus 1n plus 4. This represents the same information as that. So here I'm asking what's the 50th term, so I'm going to plug in n equals 50. And I get 7,454. But can I find out which term has a value of 756? Not yet. I can't do that. So with this type of question right now, all I can say is, all you can use that equation for is to predict the value of the nth term. And that's what this question asks. Here are two patterns. I want you to find the 12th term in each pattern. And so what you can do here is, again, you need to find the common difference. Once you find the common difference, you half that, and that's your A value. You can use your two data points to find B and C. And then once you do that, you can plug in 12. So for this case here, I have negative 16 minus 9 is negative 7. Negative 27 minus negative 16. What is that? Negative 11. Negative 42 minus negative 27. negative 15. Negative 61 subtract negative 41 is negative 19. And so I see that the common difference here is negative 4. And that means the A value is negative 2. And so I can use these data points to find the B and C value. Negative 9 equals negative 2 times 1 squared plus B plus C. 1 squared is 1 times negative 2 is negative 2. Add that to both sides, I get negative 7 equals B plus C. Then I can use another term here. I can plug in negative 16, and that's when n equals 2. So 2 squared would be 4 minus 2 is negative 8 plus 2b plus c. Add 8 to both sides, I get negative 8 equals 2b plus c. I'll take the negative 7 equals b plus c. And I'll subtract these equations. And when I do this, I'll get negative 1 equals b. And I can plug that back into right here, for instance, and I'd get c equals negative 6. So the equation here is Tn equals negative 2n squared minus n subtract 6. Now I can plug in n equals 12 to find the 12th term. So negative 2 times 12 squared minus 12 minus 6. 12 squared is 144. Times negative 2 is negative 288. Minus 12 minus 6 gives me negative 306. This one, the second question here, same idea, and you should test yourself to see if you can get the value of 433. So that's how you find the equation of a quadratic pattern. We have answered how to do how to get the equation of a deeper pattern, but it's also given us a few more questions, like how do I predict how do I guess, given a term value, how do I tell how many terms would be in that pattern? We can't do that yet. But we're going to take a break for this week on quadratics, and we'll certainly continue more of that next time. But let's take a look here at what's called function notation. Now, notation means that this doesn't make sense. It's not supposed. You're not supposed to go, oh, I get it. You know, this is just this is how we write it. Okay. For instance, well, it's a bad color because I actually don't know what that color is. But let's say that I have this. We call this red. That doesn't make sense. You just call it red. So you're not supposed to be able to figure this out. This is just how we communicate. So for instance, we were trying to find in one example there the 50th term. So we were setting n equals 50 to find T50. But we can use function notation to simplify this. Function means a relationship, and so we're saying that one relationship depends on the other. Or sorry, one variable depends on the other. So instead of writing Tn equals 3n squared minus 1n plus 4, or using x and y, I can now write the function depends on x in this relationship, 3x squared minus 1x plus 4. So f of x, this isn't f times x, although it looks like that. Because of this notation, we would just understand that this is the case, which means I'm not going to use variables like f, because that would just be confusing. So this f of x tells us that the function depends on x. And f of x is very similar to y. And so if I asked you f of 50, well, you can see that the 50 replaced the x. So this is saying, what's y when x equals 50? Or I could write f of x equals 756. This is y. So this is saying, find x when y equals 756. So let's take a look here. If f of x equals 4x minus 5, then I want you to calculate these things together. So this first thing says f of 3. Notice it's not f times 3, it's f of 3. And it was written f of x, but now this is a 3. Well, that means that x equals 3. So f of 3 would equal 4 times 3 minus 5. And that would mean that f of 3 equals 7. Here I have f of 0. That means wherever I see an x, I'm going to plug in a 0. We can do this by inspection. We get b equals negative 5. In question C, we have the opposite question. Here I don't know what the x is, but I know y, f of x, equals 3. So in question C, I'll end up solving this by writing 3 equals 4x minus 5. Right, wherever I see an f of x, we're going to replace that with the 3. That's what this says right here, f of x equals 3. So I'm going to add 5 to both sides and get 8 equals 4x. I'm going to divide both sides by 4 to get x equals 2. So I could write the answer f of 2 equals 3. And question D, similar scenario. I get f of x equals 0. Wherever I see an f of x, I'm going to put a 0. I'm going to add 5 to both sides and divide by both sides by 4. And so x equals 5/4. Now in example 2, we have two functions. We have an f of x function and a g of x function. So this is, question A says calculate g of 7. Well, wherever I see an x in the g function, I'm going to plug in a 7. So 3 minus 35 gives me negative 32. Question B asks f of x equals 7. Well, there's my f of x, so I'm going to plug in 7. I'm going to add 2 to both sides to get 9 equals 3x. Divide both sides by 3, and I get x equals 3. And then question C says, when does g of x equal f of x? Well, this is g of x, and this is f of x. When do they equal each other? Well, let's find out. 3 minus 5x equals 3x minus 2. This was like the question we had last week, where we have variables on both sides. So I can add 5x to both sides here. And I get 3 equals 8x minus 2. Then I can add 2 to both sides, and I get 5 equals 8x, and divide both sides by 5. When x equals 5 over 8, I get the same answer in both of these equations. So I get x equals 5 over 8. Solves for x in this equation. So here's a quadratic written in f of x. And so what we can do is we can find the first 5 terms of the pattern. I plug in 1 and 2 for x and 3 and 4, etc., etc. Remember that, for instance, when I'm finding f of 3, this means anywhere I see an x, I'm going to plug in a 3. Remember that this is order of operations. So I have to square the 3 first, which is 9. then I multiply it by 2. I don't have 6 times, or 6 squared. I don't have 36 here. I have 18. And so you can see that the third term is 19. The question B asks me to find f of -4. Well, again, where I see an x, I'm going to plug in -4. The pen's getting tired. So I have -4 squared is positive 16, times 2 is 32, minus 12, minus 8 gives me 12. And find f of 0, well, that's easy, that's right there. Because when x equals 0, these two terms equal 0. So what we've done today is we've been able to find the equation of 2 types of patterns. A linear pattern, where the common difference shows up right away on the first level of difference. We've been able to find the quadratic, or find an equation for a pattern where the common difference shows up on the second level of difference. And we've been able to work with function notation. So next week we'll continue with more talk on the on what exactly these quadratic functions are.